with regard to liquids, what we can think about is just the pressure forces that are acting on all the particles that are involved in the liquid, and therefore what will be acting on other things if we place them into the liquid. So if we have a container of water, and I look at some blob of the water, a little portion of the water on the inside, I have to ask, what is happening to this little portion of water? Okay. If this container is in static equilibrium, then that means that the forces acting on any certain object has to be equal in all directions. Otherwise, the object or portion of water would move around. So you'd have a current that had been set up in this if parts of this water are moving around. So if not, if everything is just stable, like you have a glass of water sitting on your table, okay, and the water is just there and not moving, then that means that all the forces acting on every single part of that water had to be equal in order for that not to be happening. Otherwise, you'd end up with a portion of that water moving around, and you'd have some kind of stirring motion, or you'd have some kind of current that is actually moving through that container of water. So that means that, first of all, horizontally, those two forces, and therefore the pressures, have to actually be equal. Okay? So, because if not, then an object would move side to side. So that's what's happening in the x direction. We look in the y direction, what are the forces that are acting on this object? The forces acting on the object are its gravitational force, so its capital M is going to be the mass, we're calling the mass of this object here, and then multiply that by g to get the gravitational force. You also have the pressure force from all the material above it acting on this thing, this portion of water right here. So the force from the stuff above is equal to pressure times area, so that there has to be some cross-sectional area we're assigning to this portion in this three-dimensional situation. And so the pressure above is pushing over that area, so the force is pressure 1 times the area. Then you have the pressure from the bottom here, again with the cross-sectional area resulting in the force pushing up. So if we look at Newton's second law in the y direction, then we can see what happens with the behavior of the object in the y direction, which, as we said, it's in static equilibrium, so it is not moving. So that means this side is going to be 0, and we have to look at what's actually happening with the sum of the forces. And we have 3 forces to include in this. So we have positive P2A minus P1A minus mg equals 0. Okay? So if I want to actually get rid of the mass and stop thinking about the area, potentially, what I can do is I can actually plug in for the mass in terms of the density of our liquid and the volume that this portion of water is taking up. So if I do that, then that means that I have P2A minus P1A minus rho for density times V for volume times G is equal to 0. Okay? So now what I'm going to do is I'm going to say this is some distance delta y. Okay? And so we have a cross-sectional area, we have a height of delta y, and so therefore those two things together are going to give you the volume. So I'm going to put that in there, so P2A minus P1A minus rho times A times delta y times G is equal to 0. Okay? So now I can get rid of all the areas, and I have P2 minus P1 minus rho times A, no, not times A, times delta y times G is equal to 0. Okay. Now, this says that P2, a pressure at the bottom of this portion of water, is equal to the pressure at the top of this portion of water plus the density of our fluid times the height of our fluid times the gravitational acceleration of the Earth, g. Okay. So this says, first of all, just looking at this, that the pressure of below has to be bigger than the pressure on top. Okay. So this is why we have a change in pressure with depth, because of how the forces are interacting and because of the weights of the stuff above and the pressure of the stuff above pushing down on what's below, and the bottom has to respond to that in order for things to actually be in equilibrium. So the pressure of things deeper under the water has to be greater than the pressure of things more towards the top of the water. Okay. And if we're saying that our portion of water is actually on the surface here, and this is our delta y, then our delta y is actually going to be the depth below the surface. And so I can rewrite that then to say that if I'm at the surface, then the pressure of anything below the surface is equal to the pressure at the surface plus rho times g times h, where h is then the depth below the surface in terms of a positive number, times g times the density of our liquid. Okay, and this P0 would be the pressure in the room, the pressure of the air above the liquid, which typically is 1 atmosphere. Okay, unless you're in some controlled situation in the lab where you increase that. And Pascal's principle says that if you do increase that pressure, then every other pressure inside the material has to respond, and so that increase in pressure gets transmitted in a uniform way, so that everything in the fluid experiences that transfer of pressure. Okay? But this is why the pressure varies with depth. If you go deeper under the surface of the water, the pressure you experience is larger. So therefore, if you're building a submarine, or some other type of deep sea vehicle, you have to end up creating the structure of that so that it is sound enough to withstand those higher pressures as you go below and deeper, deeper, deeper into the ocean. Okay? Because of all the forces acting